Welcome friends, in this one let's take a look at making a graph of 2 to the x and then also what happens when you mirror that across y equals x. We're going to get a new kind of function and we're going to look at the relationship. This is video 1. I will also put another part 2 to this video eventually up on the internet, but let's begin with this one, okay? So let's go here with f of x equals 2 to the x. This is a basic exponential curve. Okay, so let's compute. For example, f of negative 1 is 2 to the negative first, which is 1/2 by negative exponents. So then f of 0 is 2 to the 0, which is 1 by negative exponents. F of, 1 is 2 to the first, which is 2. And then f of 2, that's 2 squared, which is 4. So we've got essentially some points in here, if you think about it carefully. Let's make a graph now. Okay, so I'm going to exaggerate this graph a little bit, try to make it big. Okay, let's see here. Straight enough line gets the idea across. The axis this way. Okay, this way. All right, so let's see. This is our x, this is our y. Okay, and that's our negative y in that position there, okay? So now, let's graph this. We have to decide what we mean by distances. So like, for example, what do we mean by from 0 to negative 1, 0 to 1? I'll just make that up basically, so some space. Doesn't really matter, right? Just keep it consistent once you decide on it. So since this is negative 1, you just want to make sure it's consistent. So this is negative 1, that means this here is about 1. This here is about 2. This is about 3. And then this here is about 4. So 1, 2, 3, and 4. Okay. Same thing going vertically, right? So this is 1's units, so this would be like 1 this way, 2 this way, 3 this way, 4 this way. So 1, 2, 3, and then 4 along the vertical axis. Good. Now, let's do some points. So remember, when negative 1 goes in, 1/2 comes out. So that would be about negative 1 in, 1/2 out, roughly here, okay? That's that point. I should mark it, so let's see here. Negative 1/2 in, and then, let's see, negative 1 in rather, let me fix that. So negative 1 and then 1/2 this way. For this point, 0 goes in and 1 comes out. So this is the point, in other words, right here. This is the point 0, 1. Right, when 1 goes in, 2 comes out. So this is about the point 1, 2. I need to have a few points labeled so we can see the pattern later. And then 2 goes in and 4 comes out. So say it's about right here. So 2 in and then 4 out. Good. Now we connect. Here, I could add more points to be even more suggestive of the correct pattern to follow. But I know this, and if you check my work, you'll see it kind of works out like this, okay? It goes like this, and then goes to this point, and then it curves this way. And then the question is, what does it do past the negative 1 on the x-axis? So, for example, imagine you had like f of negative 1,000. What does that come out to be? So, this is like 2 to the negative 1,000, which is then 1 over 2 to the positive 1,000. So, 2 to the 1,000 means basically you have a huge number in the denominator, which means that this value here is approximately equal to 0. So the point is, as you go this way, what this graph does is it approaches the x-axis this way. Something really important happens though. Let me point this out. There's a gap, and the gap never goes away. See, there's a gap here, there's a gap here, there's a gap here. That gap, it never disappears. It always stays there, okay? So that's telling us that the x-axis, the horizontal axis, is what we call then the horizontal asymptote for this graph. Sometimes asymptotes are indicated by like dashing, okay? So I'm like dashing here with some red. I hope you can see that. I have to thicken it, otherwise the camera doesn't always pick up the light necessarily, okay? So that's it. This is then the horizontal asymptote. Good. In other words, it approaches the graph, but infinitely, even if you go very far to the left, there's always a gap. So on graphing software, you may not even see that unless you take a part of the graph over here when x is very negative, and then you zoom into a fine level of detail and you make these numbers very tiny here, then you will see a gap there, okay? So This gets the idea across. Now what happens, take a look, when I mirror across y equals x, the 45-degree line. That's what we want to know next. So take a look. That's going to go through 1, 1. It's going to go through, let's see, 2, 2, that point. Because when you are on y equals x, then the y and the x coordinates are the same. That's what it means to say y equals x, right? And then 3, 3, so roughly about here. Okay, and the same thing here. So since this is -1, make this -1 right here. All right, so -1, -2, here we are, and so on going down in that direction, okay? So let's make a line, the 45-degree line. It's going to go this way, this way, this way, and then this way, and then this way right here, okay? So this is our y equals x line right here, y equals x. Let's now mirror what I've just drawn across this line to the other side of it to see what happens. Now some of it is pretty straightforward. So for example, what do we mean by mirroring? That means whatever the distance is here, it's the same distance to the other side, which means that the point 0, 1 becomes the point 1, 0 right here. See this? That's what I mean. Same thing, for example, like with this point, which right now is 1, 2. Right? When you mirror it to the other side, it's got to become the point, roughly speaking, let's see, 2, 1. Okay, so that would be like the point 2, 1. So then you draw about the same thing to the other side of that line. About, so it's about here. So this is the point 2, 1. Okay, good. So now take a look. What else do we have here? We have the point 2, 4. So that's this thing here. If I mirror that across to the other side, it's about like that. Yeah, eyeballing it. So it then becomes the point 4, 2, which is maybe about right here. So this is now 4, 2. Okay? We can connect these already with a smooth line, you know, with a bit of curvature to it, and then it kind of shoots off this way. Now the question is, what happens with these? So since this is -1, 1/2, then the new one would be 1/2, like this, as the x-coordinate with a value of -1. So that would be down here. Okay, so then we can continue to connect. But now, what happens to this gap? That's what we want to know next. Well, the gap cannot just disappear. It just becomes, instead of being a horizontal gap, it just becomes a vertical gap. So let me explain that to you, okay? Imagine you take this point here, whatever the y-coordinate there is, okay? Maybe it's a quarter, roughly speaking. So that means, take a look at it, right? So this, let's say this is -2 about. So you'd have -2 as basically your input into the exponent. So you'd have, in other words, 2 to the -2nd, which is 1/2 squared, which is a quarter, you see? So -2 goes in and a quarter comes out. So that means on the other side, when a quarter goes in, -2 comes out, like this. You see this? So the point is that whatever the gap is here, that gap is now being made into a vertical gap, so to speak. And it never goes away. So as you grab other points from here and here, say at -3, right, -4, and so on going this way, all you're going to do is make this -3, make this -4. You're just going to reproduce the gap. The only difference is the gap is vertical, but it doesn't go away. That's the big idea here. Let me stress that, okay? So, in other words, what is it saying? It's saying that for 2 to the x, the x-axis is the horizontal asymptote, this little gap that never goes away. For this new graph, that's the mirror image of 2 to the x across y equals x, the vertical axis is now the vertical asymptote. In other words, here, right, there's always a gap. It doesn't matter how far down this way you go, okay, there's a gap. Some software will make it seem like the graph overlaps the vertical axis, but that's just a problem with the resolution of, for example, the graph more than anything else, or the screen. If you focus on just a part of this in your software, and then zoom in to a very fine degree of detail, very, 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 fine degree of detail, you will see even then some software can still show there's a gap. There's always a gap present here, okay? So that means for this new graph, this one here, the vertical axis now is the vertical asymptote. So what is that telling us? Well, it's telling us, take a look, for 2 to the x, the domain is negative through positive infinity. Any value of x that you can imagine, you can plug into 2 to the x, no problem. For the new one here that we've just generated, it's different. X equals 0 can never be plugged in because there's always a gap between the graph and the vertical axis, which means the vertical axis is never crossed. So that means x equals 0 right here is not part of the domain, nor any of these negative values, right, for this graph. You see, the graph never crosses the vertical axis. It never touches it, nor does it ever cross to the other side, which means for this new function, domain is x is greater than 0. And again, this is all premised on the fact that the horizontal asymptote of 2 to the x becomes the vertical asymptote of this new graph. And now this new function, and this is a function right here, because it passes the vertical line test, don't forget that, right? The word function in math has a very specific and concrete and precise meaning. So this new one then is called log base 2 of x, right here. In other words, it's base 2 because here I have a 2 in this position as the base. So now that number goes into this position as the base on the logarithm. In the next video that comes with this, I'm going to talk about making use of log base 2 of x and also some other slightly more abstract concepts relating to the relationship between 2 to the x and log base 2 of x. But that's in the next video. For this one, just keep in mind, I've done this for 2 to the x, but if I did a picture for 3 to the x, it would look very similar. For 4 to the x, it would look about the same. These concepts that I've developed using one specific function carry over to basically a lot of functions of the form where you have a, some number in the base, and the variable is an exponent. But that's it for this one. So the next one, I'll add more stuff on the, let's see, on the right side here. So please leave a like, please subscribe. Thank you so much for watching, and I will see you in the next one. Leave some comments down below.